let's look at using our function notation with tables, keeping in mind that for every input, there's exactly one output. Or you can think of it as for every x value, there's exactly one y value that goes with it. So kind of what we talked about before, determining from a table whether or not is a function, we would just focus on our x values, and we want to be careful of any repeats. So for this first function, f of x, we can see we have all unique x values, so that'll be a function, yes. With our second function, 1, 4, -2, 1, so I see that I have x equals 1 show up twice, and it goes to different outputs. So with that, that is not a function. So for our input, it maps to two different spots, which we can't have. So that's it for that table. That one's done. We're going to focus on this first table for answering some questions. So looking at f of 1, what this is asking is we know that x equals 1, and we basically want to know what is the output. So to read that from a table, what we would do is look at where x equals 1 and see what the matching output is. So what I would do is look at x equals 1, and I can see the matching output is that positive 1. So we have the value 1, 1, and you can see how it makes a coordinate as our tables list out of that coordinate 1, 1. F of 4. So we're looking at x equals 4. So I just look for my x value, and then I just want to write down the matching output, which is the positive 2. So we can see our coordinate 4, 2. F of 6, we'll look for x equals 6, but what we'll notice is on our table, we don't have x equals 6. So we can't plug that into our function, or since we don't have the function itself, we don't have the equation for it, we don't have anything to solve. So in terms of a table, what we would say here is that it just does not exist. So you can use DNE for short, or you can write out does not exist. All right, so I'm just going to separate this table a little bit because we're going to move on to using the table in kind of opposite direction. But with these first three cases, it's the idea of given x and then grabbing the output from our table for f of x. In these two cases, we're given f of x. So the idea here is going to be that we're given our y coordinate, we're given our y value, and what we need to do is find what is x. Now these solving cases where we're plugging in for y, we can have more than one solution. We might see multiple values for x. We might see just one value. We might see no values. So with that, we're going to find x for the spots where we have an output of positive 1. So looking at our table, now I'm looking at the other row where I'm looking at the f of x values. And what I can see here, in fact, I'll highlight them. Here's an output of positive 1, output of positive 1, output of positive 1. So what I want to do is grab the matching x values. So I'm going to have x equals -1, positive 1, and 3. So x could be -1, positive 1, or 3. So if I wrote this out in function notation, it would be that I have f of -1 is equal to positive 1, f of positive 1 for x equals positive 1, and f of positive 3 is also positive 1. Again, just to emphasize, we can have these different x values mapping to the same output. That's totally fine because we're not repeating x. All right, this last one, what we'll see is we're looking for positive 6, but as we go along that row there, we never have an output of positive 6. So with that, we don't have a solution. So we just say no solution. Since we don't see that as an output on our table. All right, Let's look at a table as a word problem. So what we have here is we're getting values I, which is representing the number of Americans with internet access in millions, and we calculate I based on the function m of t. T is representing time in years after 1950, and what can help with these questions where we treat time as this number of years after the starting point, you could just make a note next to the table. So like 0 would represent 1950, so having t equals 45 would be 1950 plus 45. So there's 1995, here's 1997, 2000, 2005. So even though algebraically we would work with these values of t, and having those small numbers can just make the calculations a lot easier, in terms of interpretation it can help to make a note of this so you know which years you're working with. And then these m of t values, these are what I represents, which is this number of Americans with internet access. And we'll just want to keep in mind that the units are in terms of millions there. So if I want to find m of 45, so 45 is my value for t. So what I would do is go to where t is 45. So my function output is 40. So 40 would be this number of Americans with internet access in millions. So to make my sentence there, t equals 45 means 1995. So I'm going to make a sentence that says something like 40. Oh, I don't really want to write this in blue. I'm just going to change my color. All right, 40 million Americans had internet access in 1995. All right. Looking for m of t equals 172. So what we're trying to do is find what value for t do we need to get 172. Again, this idea of solving for our input value, we might end up with more than one answer. As we can see from our table, this output of 172 only occurs once, and it occurs when t is 55. So now we know t of 55 gives us a value of I for 172. So I can kind of match my sentence structure up above there. I'll say 172 million Americans had internet access in, and then 55 is the equivalent of 2005. All right, so that's how we read our input and output values for our functions from tables.